Hello, John here again with another video. This is tutorial 12, I think, and after I did the bit manipulation tutorial, I think it was tutorial 9, when I was explaining how to logically shift right and rotate right and add with carry, and I used an example which was a 16-bit multiplier as the code example. Well, I've been private messaged and asked if I could do the 16-bit divider as well, instead of just saying that the divider was the opposite of the multiplier and using the logical shift left and rotate left. So I thought I'd leave it a couple of weeks to see if you guys could figure it out, but here we are, and this is the logical shift, the bit manipulation part 2, which is the shifting left instructions. So the first instruction is the logically shift left. Now, logically shift left is exactly the same as logical shift right, but doing it left. So what it does, it inserts a 0 into the least significant bit, and then pushes and shuffles every bit over left by 1, and the most significant bit is then dropped into the carry flag. So instead of with right, it's a 0 is injected into the most significant bit and then shifts right, and then the least significant bit drops into the carry. This is the other way around. So effectively, when you execute this command, it's effectively times in the number by 2. So if you had a 1 in bit 3, which is 1, 2, 4, 8, the number 8, if you logically shift left once, then that becomes 16. So effectively you've times 8 by 2. The other one is rotate left, and the difference between logically shift left and rotate left is rotate left injects the value, the state or the value of the carry into the least significant bit, and then everything shuffles left 1 bit, and then the most significant bit then is dropped into the carry flag. And it's exactly the same methodology as logically shift left, but the difference here is if you carry on executing the command without changing any of the states, you'll end up with the same number again after 8. The subtract with memory with carry is exactly that. It subtracts the memory from the accumulator with the carry. So if your carry is set to 1, then it won't subtract the carry, because remember, it's doing the opposite of add. So if you had the carry was set in add, it would add 1 as well. Well, the subtract is the reverse. You have to set the carry to make sure you don't subtract 1 more than you should do. If the carry is 0, it will subtract 1 more. So for example, if your carry is set to 1 and your accumulator is 10 and your memory location is 3, it will be 10 minus 3 equals 7. And because your carry is set to 1, it won't minus another 1. But if your carry is set to 0, the same scenario would be 10 minus 3 equals 7, minus the carry, because it would have been set to 0, so you borrow, and then it becomes 6. So a typical division, or long division, in decimal is something like this. So you have 185 as your number, and you want to divide it by 14. Now the way you do long division, you say, does 14 go in? Is 1 divisible by 14? The answer is no. So you put a 0, and then you move down another digit, and then you say, is 18 divided by 14? And the answer is yes, and it's divided by 1 with 4 left over. Yeah. So once the 4's left over, then you bring down the 5, and then is 45 divisible by 14? And the answer is yes, and so you do it You divide it by 14. Can you do it again? Yes, I can. Can you do it again? Yes, I can. So that's 3. So the next answer digit is 3. And it leaves you with 3 as a remainder. But because the number stops then, the routine would finish. So your answer is 13 with a remainder of 3. We can represent that in code. So here it is. Here's the the flow chart for a divider. So we start, we've got our answer and we've got our number to divide and our divider. So we set our answer to 0. We set n to be 8 because remember we're doing, if it was an 8-bit divider, we have to run through it 8 times, or if it's a 16-bit divider we have to run it through 16 times. So then -1 off the counter, we logically shift left, so we effectively times into the most significant bit, high byte. The most significant bit then drops into the carry, and then we subtract that from our number. So we subtract to give us an answer. And if the carry was set afterwards, that means that we managed to subtract our divider from our number, and so we increase the result by 1 because we've managed to subtract it. If it was clear, then we haven't managed to subtract it, so we bypass that and then go to do the loop again. Once we've increased the result, we test to see if our indexer is set to 0. If it's not, we loop back round again, but if it is, we jump back out and our final answer is in the answer and our remainder is in the remainder. So we can look at this using code. So here is. So we've got the standard basic code, which is to do sys 2304, and you guys should be used to this by now. My header, so I'm starting at 0900. I jump straight to divide. I include some of my common assembly routines for the tutorials. I've got the strings to show on the screen, so please enter a number to divide by, and the result is with the remainder of. And then we've got our routine, our divide by routine. So we're going to divide a 16-bit number by a 16-bit number. So we've got the divisor, the divide end, that's the number, the remainder, and the result is equal to the divide end. So the code is, right, add a line to the screen, print out or display, enter a number. So we get a 16-bit number, then we store it, and then we add another line and then get the divide by, and we get an 8-bit number this time and we store it in the divisor. We initialize the remainder and we load the counter for 16 bits because remember the number is a 16-bit number. We then start the loop, so we logically shift left the number that we've typed in and roll the high number, so effectively multiplying it by 2. If the carry is set, we roll it into the remainder and the high by to the remainder, and then we load the remainder up. Set the carry, because remember to subtract, carry must always be set to successfully subtract properly. We subtract the divisor. We transfer the accumulator into Y because we need to keep that number steady. We load the remainder plus 1, and then we subtract the divisor plus 1. So we're subtracting a 16-bit number from a 16-bit number. If the carry is clear, then it means that we couldn't subtract it, and so we have to jump round and do the next one. But if it wasn't clear, that means it was a perfectly good subtract, and we managed to subtract the divisor out of the number, and so we store that number back into the remainder. We store the original number here into the remainder low byte. We increase the result by 1 because we've managed to subtract the number from the number successfully, and if the result is not equal to 0, then we skip this. But if it is equal to 0, that means we've crossed the page and we need to increase the result plus 1. Here we are where we decrease the counter, and if it's not equal to, we go back and loop again. If it is equal to, that means we've done the 16 bits, and then we just print out the results here and here, and then we jump back to basic. So shall we try and see how it does it? So here we go. So it's asking for our number, so we're going to do an easy one. So 16384, and we'll divide it by 100. So that should give us 163 with 84 remaining. There you go. So if we do another one, so let's try 1, 2, 3, 4, 5 divided by 105 gives us 223 with 41 remaining. So let's try that out. So here we go. So 2, 3, 4, 5, 6 divided by 105 equals 223. Now I've got this set to integer, so that's why it's not showing the reminder. Because if we do 223 times by 104 or 105, we don't get the same number. So let's put this back into standard. There we go. So 2, 3, 4, 5, 6 divided by 105. Now our 223.39. So I'll put it back into. So I'll try a different one. So I'll run it again. So let's try 3, 4, 5, 6, 7, and we'll divide it by 23. There you go, 1,502 with 21 remaining. So there you go. So some very small routines. In this particular case, this is the dividing routine, but you've also got the multiplying routine. So these take 16-bit numbers. You'll be able to multiply to give a 16-bit number, or divide to give a 16-bit number. So I hope that this tutorial has been informative, and I'll see you on the next next teaching tutorial. Take care. Bye.